Welcome to Analytical Chemistry classes. Here, we will see the second part of solvent extraction or liquid-liquid extraction. In the first part we have learned the definition of solvent extraction, theory and mechanism by which solute molecules are extracted, the purpose of extraction, determining the percentage extraction, some numerical problems related this topic. In this part, we will see the methods of solvent extraction, where we will see how the different way in which the solute or chemical substances can be separated from one solvent system to another for the purpose of purification of concentration. Let us see the methods of solvent extraction. There are three main types of solvent extraction methods by which solute that organic or inorganic substance can be separated or isolated. The first one is batch extraction, second one is continuous extraction, and third one is countercurrent extraction. Let us see what is batch extraction and how it can be used for separation of solute. Batch extraction is the simplest and most commonly used method, consists of extracting the solute from one immiscible layer into other by shaking the two layers until equilibrium is attained, after which the layers are allowed to settle before sampling. This is commonly used on the small scale in chemical laboratories. The apparatus used for batch extraction is separatory funnel shown here, which is low cost and easy available. See here the examples of batch extraction for separation of nickel, chromium, lead, copper ions from sample solution. A. In the image shows the formation of nickel with DMG, dimethyl glyoxime, which is organic reagent. B. In the image shows the formation of chromium with diphenyl carbazide, DPC, and C. In image shows the formation of complex with lead ion with dithiazone, and finally, the D. In the image, complex of copper with neocuprone, and these complexes can be extracted using organic solvents such chloroform, hexane, petroleum ether from aqueous solution, or aqueous solution of soil, or aqueous solution of food samples. Further, these separated extracted metals ion can be used in visible spectrophotometry or atomic absorption spectrometry. Here, we can see how the batch extraction can be performed using separatory funnel, shown in the image. The extraction of organic and inorganic components from aqueous solution of soil or food, etc. are done many number of times until the maximum extraction or separation of target substance from solution. Now, we will see the continuous extraction. Before we should know, what will be limitation of batch extraction? The limitation of batch extraction is use of large amount of solvent needed in separatory funnel. Therefore, there is need of another technique which use small amount of solvent and can be reused. This method is used when an organic compound to be extracted has nearly the same solubility in water as well in the organic solvent, i.e. the distribution coefficient between the organic solvent and water is small. A large quantity of organic solvent is employed to obtain even a moderately efficient extraction. This can be avoided by continuous extraction using an apparatus known as continuous extractor where a very small amount of solvent is required. First we will see the figure, which is apparatus used when the solvent heavier than water for extraction of solute from sample solution. Here the B, shown in the figure showing round flask containing heavier organic solvent and a part of the apparatus containing sample solution with solute substance. First, the round bottom flask, B, is heated and solvent molecules get vaporized, and goes upper part of the device and then with the help of reflux condenser the solvent molecules get condensed and passes through the aqueous solution containing solute substance dissolvent into the immiscible organic solvent. After increase of this extracting solvent in the bottom of flask, A, it passed again to round bottom flask, B, again continuous heating of organic solvent and vaporization and condensations. This process continues until the maximum extraction of substances takes place with solvent. Next, we will see the figure which is apparatus used when the solvent is lighter than water for extraction of solute from sample solution. Here the B, shown in the figure showing the round flask containing heavier organic solvent, and A, is part of the apparatus containing sample solution with solute substance. First, the round bottom flask, B, is heated and solvent molecules get vaporized, and goes upper part of the device and then with the help of reflux condenser the solvent molecules get condensed, and passes through special tube, C, shown in the figure. At the bottom of the tube, organic solvent escapes out, and droplets of organic solvent moves upside due to lower density. In addition, when it contacts with aqueous solution, the solute molecules get diffused into organic solvent, and finally reaches up, and then again passes to round bottom flask, B, Again, continuous heating of organic solvent and vaporization and condensations. This process continues until the maximum extraction of substances takes place with solvent. Now, we will see another third type of solvent extraction methods, that is counter-current extraction. Before we should know, what is the limitation of continuous extraction? The limitation of continuous extraction is only used for separation of one solute at a time. Therefore, there is need of another method which should separate more than one solute from sample solution. Thus, countercurrent extraction is employed. This is also called as multiple liquid-liquid extractions, which permits the separation of substances with different distribution coefficients, ratios. A clever design known as Craig apparatus is used for this purpose, Lyman C. Craig, 1943, shown here. Craig apparatus consists of a series of glass tubes, R0, 1, Do, that are designed and arranged such that the lighter liquid phase is transferred from one tube to the next. The liquid-liquid extractions are taking place simultaneously in all tubes of the apparatus, which is usually driven electromechanically. In the following animated picture of a single glass tube, the typical extraction transfer cycle is shown. Here, we will see what is mechanism for separation of solute molecules in multiple glass tubes in Craig apparatus, based on Nernst distribution law. Suppose the distribution of a substance A in each tube after a given number of equilibration, transfer cycles, and volumes of each solvent are equal to V, and let W represent the weight of A in the sample, P and Q represent the fraction of A with distribution ratio of D in the upper, organic solvent, O, and lower, water, W, phase. Then it is, D is equal to concentration solute, A, in organic solvent by concentration solute, A, in aqueous phase. Similarly, there will be the ratio of fraction of solute in organic and aqueous phase, P by Q, since P plus Q is equal to 1. Then P is equal to D by D plus 1, and similarly Q is equal to 1 by D plus 1. And side pink and colored boxes show the fraction of P and Q distributed after several number of cycles. Finally, we'll see the formula for determination of fraction of solute after n number of transfers, cycles, and since the ratio D equals P, Q must be maintained for each tube after the equilibration step, the total fraction of R in each tube corresponds to the terms of the binomial expansion, P jod Q, n. Therefore, the total fraction of solute in tube R after n transfers equal to n factorial by R factorial into bracket n minus R bracket of factorial, multiply by D to power R by D plus 1 to power 1. Thank you for watching the videos on analytical chemistry. Please see the next part of solvent extraction part 3, and if you not seen part 1, please see, and if like such videos, please like it and subscribe it.